The end Permian extinction, December 12th. If it isn't evident at this point, it will become more obvious within the next couple of slides that factors governing climate change are complex and numerous. There are many variables and many chain reactions that can occur. Sometimes the reactions are so severe they spiral out of control. The end Permian extinction was one of the biggest extinction events the Earth has experienced to date. It set the biological clock back 300 million years, or all the way back to the beginning of the Cambrian, late in the day on November 18th. Scientists believe the extinction event was due to a very large, long-lived volcanic eruption which had several pulses. This would be the eruption of the Siberian Traps, the largest eruption that has occurred in the last 500 million years. The 2-million-year volcanic eruption resulted in an estimated 1 million cubic miles of lava. Carbon dioxide accompanied the lava and was released in large volumes into the atmosphere. As the carbon dioxide accumulated, temperatures started to rise. As things got hotter, ice caps began to melt, and as the ice caps melted, pressure was released on methane reservoirs. This caused the release of methane into the atmosphere as well. This, coupled with the Earth's decreasing albedo, caused even more warming to take place. As more ice caps melted, the Earth's albedo decreased even further, and it began to really absorb the rays, causing temperatures to rise, which ensured any ice that was left was melted, which totally decreased the Earth's albedo, ultimately resulting in a hot greenhouse Earth. The temperature rise would kill off many plants, which would in return kill off many animals due to a lack of food, well, along with the heat. Trade wind modification and rising ocean temperatures would cause rainfall to increase, which would be even more severe in nature, causing large floods and large amounts of debris to be eroded off the continent. Eroded material would include the recently deceased, which would be carried out to sea. Again, we have given the ocean a dose of our multivitamin, and a massive algal bloom was soon to follow. The algal bloom would consume large quantities of oxygen, causing anoxia. The continental, oceanic, and algal biomatter would begin to decay, also consuming oxygen, exacerbating the anoxic environment, making it nearly impossible for life to hang on. This, coupled with limited sunlight, would result in the death of many or all organisms living below and slow or stop photosynthesis. This would cause carbon dioxide levels to continue to rise, and in the ocean, this would create yet another problem. Ocean acidification. Limestone is a common rock variety that is made up of calcium carbonate, or the shells, skeletons, and ooze of calcareous sea creatures like corals. If you take any kind of acid, be it vinegar, lemon juice, hydrochloric acid, and drop it on the rock, you will see that it starts to bubble. You are effectively dissolving the rock. The same thing happens when corals and other organisms that use calcium carbonate for their skeletons or shells. Given enough acid and enough time, there would come a point when the skeleton would completely dissolve. Ocean acidification is not a good thing if you happen to be a coral or a shelled creature. Well, let's be honest, not many organisms like and can survive in acidic conditions. So how is ocean acidification achieved? Well, there are two main ways we will look at. As the CO2 from ongoing volcanism accumulates in the atmosphere, it gets absorbed into the ocean. Through a series of complex chemical reactions involving CO2, the hydrogen ion concentration increases, which decreases the pH of the oceans, causing acidification. Calcareous skeletons start to dissolve, and organisms are unable to make their skeletons and die. This will be the same scenario for the other two possible causes of ocean acidification via acid rain we will now discuss. CO2 is not the only gas to be released during volcanism. Let's focus on sulfur dioxide. Sulfur dioxide gas, if present, which it was, will accumulate in the atmosphere as well. Sulfur dioxide will bond with water to form acid rain, right? Not good. The most direct route for acidification of the ocean via acid rain is pretty obvious, acid rain pouring down on the ocean. The other way is similar to what we saw in the anoxia example, only a bit more sinister. Whatever vegetation may have been left after the initial warming event would be destroyed by the acid rain, as would the topsoil. With most of the remaining plants gone, several more animal species would meet an untimely demise. With the plants out of the way, erosion may now kick into full gear. And with all that acid rain coming down, it will now easily wash all of the acidic material into the oceans, acidifying it even further, killing even more organisms. We have yet another blow taken to the photosynthetic process in the ocean and the ability to fix the ever-increasing CO2 levels from the ongoing volcanism. But wait, there's more. Ozone depletion is all about atmospheric chemistry. Volcanic eruptions have the potential of releasing large volumes of particulates like ash, halogens, and hydrogen chloride into the atmosphere. Scientists have found that particles or aerosols produced by major volcanic eruptions accelerate ozone destruction. Particulates from volcanic emissions do not directly destroy the ozone, but they do provide a surface upon which chemical reactions can take place. This enhances chlorine-driven ozone depletion. So when the ozone is depleted, more radiation penetrates the Earth's surface, which, as we know, has severe and/or fatal effects on living organisms, including plants. We learned earlier that too much oxygen oxidizes methane to CO2. Well, when too much sulfur dioxide is present, it stops or slows the oxidation process from happening, and as a result, methane levels increase as it is no longer being converted to CO2. Remember, methane can hold way more heat than CO2, and with that, the thermostat goes up. So what did we end up with? Remember when we first started discussing the Permian extinction? It was stated that there were several pulses of volcanic activity. Some of the events we just looked at occurred more than one time, sending the planet into a serious downward spiral, justifying the reason this event is referred to as the mother of all extinctions. Again, we ended up with a really hot planet with lots of carbon dioxide and only minimal means of sequestering it. Recovery is hard to define. It was geographically specific, and numbers range from 1 to 10 million years, as there were some intermittent setbacks along the way. I can hear you asking, well, where did all the CO2 come from? There has been evidence found that the magmas of the Siberian traps intruded into and incorporated coal and other organic material, which according to researchers would account for the high CO2, sulfuric acid, and acid rain along with ozone-destroying halocarbons.